Good morning, champs. Today, we're going to build a complete solution strategy for one of the most important problem types in fluid dynamics, laminar flow derived from the momentum balance. This is not about memorizing formulas, it's about knowing exactly what to do when you see these problems, every single time. We'll start from first principles, stay fully general at the beginning, and only later decide what kind of fluid we're dealing with. That mindset is the key. First, let's define the geometry and the control volume. We are looking at steady flow in the x direction. The velocity only depends on the radial coordinate r. To derive the governing equation, we take a differential cylindrical control volume with radius r, thickness dr, and length dx. The flow direction is x, not r. R is just the direction in which stresses vary. Now we do the force balance in the x direction. No assumptions about the fluid yet, just physics. There are three contributions. Pressure forces acting on the faces at x and x plus dx. Shear stresses acting on the curved surface at radius r and r plus dr, and inertia. But since the flow is steady and fully developed, there is no acceleration in x. Writing the balance and dividing by the volume leads directly to the governing equation, dp over dx minus 1 over r times d of tau times r over dr equals 0. This equation is extremely important because it links pressure gradients and shear stresses without assuming any fluid model. Next step, integration. We rearrange the equation and integrate with respect to r. Doing this carefully gives the general shear stress distribution. Tau equals minus dp over dx times r over 2 plus c1 over r. At this point, the result is still completely general. It applies to Newtonian fluids, Bingham plastics, and many others. We haven't chosen a fluid yet. Now we choose the constitutive law. Here we explicitly assume a Newtonian fluid, because it's the most common case. For a Newtonian fluid, shear stress is proportional to the velocity gradient. Tau equals viscosity times du over dr. Substituting this relation into the shear stress expression and integrating again with respect to r gives the general velocity profile with two integration constants. This is where you see the r squared term, the logarithmic term, and c2. Now we apply boundary conditions, and this is where many mistakes usually happen. First boundary condition, symmetry at the center line. At r equals 0, shear stress must remain finite, which forces the logarithmic term to vanish. This immediately gives c1 equals 0. Second boundary condition, no slip at the wall. At r equals r, the velocity is 0. Applying this condition fixes the remaining constant. After simplification, we arrive at the final velocity profile. U equals minus dp over dx times 1 over 4 viscosity times r squared minus r squared. This is the classic parabolic velocity profile for laminar pipe flow. Now do a quick physical check. If pressure decreases in the flow direction, dp over dx is negative. That makes the velocity positive everywhere, with a maximum at the center and 0 at the wall. So the physics makes sense. And that's the full strategy. Define the geometry, choose the correct control volume, write the momentum balance before choosing a fluid model, integrate once for shear stress, choose the constitutive law, integrate again for velocity, apply symmetry and no slip boundary conditions, and finally check the signs and physical meaning. If you master this sequence, you can solve laminar flow problems in pipes, between plates, and in many other geometries, even when the fluid model changes. In the next video, we'll apply this exact same framework to different geometries so you can see how universal this approach really is. All right, champs, that's your one-stop method.